Express in ADRS format. What is ADRS? SA versus SD. Acceleration, displacement, response spectrum. So this is also a response spectrum, but it is in terms of acceleration and displacement. Response spectrum you can plot in terms of acceleration versus time period, velocity versus time period, displacement versus time period, acceleration versus displacement. Okay, and our typical capacity spectrum will look like this, whereas the demand spectrum and we discussed how to obtain the performance point. So performance point corresponds to a displacement here at which, if I consider the historetic loop, okay, then I can calculate xi equivalent as xi naught plus 1/4 pi Eg over Es. And then if I reduce the response spectrum with this Rxi, which is a function of xi, and this Ed is area of this historetic loop, and Es naught is this. This is Es naught and this is E. Okay, so we have to satisfy the capacity, demand and time. That point which satisfies these three, okay, this is performance point. And what is this performance point representing? It is representing the resultant response during given earthquake. And what is that given earthquake? Which is represented by this response spectrum. So if I know the target response spectrum at any site, okay, I can calculate the displacement which will occur in my structure under that earthquake. Any doubt up to this point? So this point we have to obtain iteratively. Okay, we will assume some displacement, then calculate the historetic damping 1/4 pi Ed by Es naught. Then we will calculate the reduction, and this Rxi, the reduction factor for response spectrum. This I have given you, plus xi equivalent to the power 1/2 or 0.5. Yes. Sorry, and we are. This will not decrease. Actually, this will also decrease. So, no, yes, it is right. It will not decrease, because when you are increasing the damping, okay. So you can see for different damping, here we are not reducing the hazard, we are increasing the damping. So due to damping, the reduction factor is such that PGA remains same. PGA is not affected by, because what is this value? EPGA. EPGA is representing PGA. So EPGA does not change with damping. Whatever damping you take, it will remain same. So for very high frequency, that is very short period, okay, t when it is less than 1/33 second, then effect of damping is not there. So response spectrum changes only in this way. Actually reduction here and here is also different if you go into more detail, but we were using this uniform reduction in acceleration and velocity control range. Okay, so from here to here it is R side. Here it will be, the response spectrum will be drawn in such a way that it joins the EPGA same as in case of 5%. Okay. SDP we are obtaining, we are not deciding. We are obtaining. We have to obtain in such a way. That's why we have to do iterative procedure. Okay. And what is the iterative procedure? This is our capacity spectrum. We will represent this by equivalent bilinear response. Equivalent bilinear response spectrum will be obtained in such a way that this is SA and this is SA dash. What is this SA dash representing? First. Okay. If first yield is not known, because you will be having capacity curve and first yield is not known, then you can take it in such a way that this SA dash is approximately 0.7 times or 0.75 times SA. Okay, different people have taken differently. SC41 suggested like this. So whatever is this SAY, 0.7% of SAY will be this SAY dash. Okay, and then the area under the two curves, this area which you have included should be same as this area which you have excluded. So that will become equivalent bilinear. Okay. Then demand curve for 5% damping, the demand spectrum. This is corresponding to 5%. Then what you will do? You will assume a trial value of ST. Can you guess what will be the closest value of SD1? If I have to choose this SD1, how should I choose? Can you guess? What is a good guess of the displacement during earthquake? Let us assume equal displacement principle. What does equal displacement principle tells us? We are trying to obtain the non-linear response, non-linear displacement of that. Equal displacement tells us that it will be close to linear displacement. How can we obtain linear displacement? From here. This is our what we call P effective period. Okay. So if I extend this, where it is intersecting, what does this give me? You remember any line passing from the origin, what it is representing? Constant T line, and its period is same as the initial period of my structure. So where it will intersect, that is the elastic period, elastic displacement. Elastic displacement. So I should choose this SD1 close to this SD or same as this SD. My performance point also will be somewhat near to this. So I can choose this as the first track point. Okay. So when I choose this as the first trial point, what I am going to do? From here I will develop the hysteretic loop, and for bilinear system this will be a parallelogram. I can calculate the area of the parallelogram. How to calculate area of the parallelogram? How to calculate area of a parallelogram? You can consider that consisting of 4 parallelograms. You can see these 4 parallelograms are equal. So calculate area of one parallelogram. So if I have to calculate area of this parallelogram, this is SAY, okay, this is TE, okay, slope. Can you calculate area of this parallelogram? You need this slope of, let us call that is alpha times T. Some fraction times. Okay, if you remember the pushover curve, VB versus delta rho. So this is representing the elastic stiffness KE, and this stiffness after E we can represent it by alpha KE. Same alpha, because mass remains same, so same alpha is there. This alpha and this alpha is same. So can you write down equations for this? Can you obtain the area? How you are going to obtain the area? Tell me the method. It's a geometric problem. Think how you are going to obtain the area of the parallelogram. Once you have obtained the area of the parallelogram, you can calculate xi hysteresis or xi equivalent itself as 0.05 plus 1/4 ED over ES. And then you can calculate RXi, and with that RXi you will reduce okay, so you can see that the 2 points are not matching. So what you have to do, next point you will take somewhere in between. This will be our SD2. This will be between the original point which we have taken as SD1 and where I have got the intersection. Then what I can do, I will consider a new hysteretic loop. Area of this new hysteretic loop is going to be larger than the previous hysteretic loop. So the damping will be more. If damping will be more, the reduction will also be more. And the new response spectrum may be like this. Because the damping is more, so this R by 2 will also be more than R psi 2. And then it is possible that it intersects at this point. If not, you will take another point and you can see in successive iteration the range between the intersection and the original point which you have selected will go on narrow, and finally it will be converge. And you will get this point which we are calling as DP or performance. This is important. R high value is less. R high value is less. So this will be lesser fraction of that. Let me put it like this: 1 upon R high. Because this formula which I have given, there are two types of formula available. One are giving R high greater than 1, means you have to divide that by value 1. If R high value you are getting greater than 1 using some formula, what does that mean? It means it is asking you to reduce by that factor. And if R high is a fraction of 1, that means you have to multiply. Okay. So the R high which this formula is giving, which I have given you, will give a fraction of 1. Okay. So that will be smaller. So reduction will be more. Is this process clear to you? This method of obtaining performance point, this was the first method and it was given in ATC 40. So this is also called ATC 40 method. Okay. Problem is that this method is identical. If you want to read in more detail, you can look at ATC 40 document we have already given. This was ATC 40 was the first document which talked about performance based design and obtaining performance point like this. Now it is known that this method is not accurate. This method has become obsolete. It is not accurate. And in FEMA for FEMA 440, there was a modified method, MADRS, modified acceleration displacement response spectrum method, where this method was modified to get more accurate results.
Sir?
Yes.
I am reducing the actual response spectrum to the response spectrum need. What points you need to reduce? What points you need to reduce?
What point? Whole graph. Whole graph in this range. Beyond this range. You will multiply by that one. Beyond this point. Okay. This point will be joined by the EPG. This is not going to be. So slope of this line will go on changing.
Then why the length of this is changing? Length of the bracket is changing.
Because you are multiplying by factor, so that will reduce.
I mean, but the length will remain because there from that point to this point and then length same.
Okay. So this will come from intersection of this and this. So if you keep this same, then this ratio will not be same. So this will be obtained from intersection of this, which is proportional to 1 upon t. That you have to modify. Okay. So wherever that intersection you are getting, this intersection point, this period may not be same. Okay.
first we have to modify this right side.
So first you have to reduce this by multiplying by r, then you have to reduce this multiplying by r wherever these are intersecting. That will give you the new coordinate. Okay. Any other doubt?
Will you summarize the steps first? That thing is clear that first we will plot the capacity curve, then we will get one response spectrum.
First we will plot the demand and capacity.
Demand and capacity.
What is demand? Demand is 5% damped elastic response spectrum. What is this 5% damped elastic response spectrum? Which is given in the code.
Yes.
Or if you are considering at some site, then you can obtain this from PSA.
Yes.
So you will obtain 5% damped elastic response spectrum for which you want to calculate the response of your structure.
Yes.
Okay. Then you will plot capacity curve.
Yes.
Convert that into capacity spectrum. So you have capacity spectrum and demand spectrum corresponding to 5% damping.
Yes.
Now you assume some value of target displacement. Okay. The closest guess can be based on equal displacement principle, where you can get the elastic displacement and consider your plastic inelastic response same as the elastic response. That can be a good guess. And how to obtain elastic response corresponding to any period from response spectrum in ADRS format? So we discussed that this is our response spectrum, and any T line, if you draw here, okay, it will be like this, and the corresponding displacement, what will be this? This will be
Yes.
displacement corresponding to period T1.
Elastic displacement.
Elastic. So we will calculate this elastic displacement like this, where T1 will be the initial period of my structure. And what is the initial period of my structure? Which this first line is there. Okay? So we will consider this. Not this one. What is this giving us? It should be very clear that when you will apply dV versus delta roof curve you will obtain, you will get something like this. Okay. This we call, if I draw a tangent here, this is Ki, initial stiffness. Okay. But what we plot is we join this point with the first yield here. This stiffness we call equivalent stiffness Ke or effective stiffness. This Ke depends on the crack section. If you are not considering crack section, then you will get this Ki. So Ki will depend on what gross stiffness, what fraction of gross stiffness you have considered as effective. Okay, so this will depend on EI effect. And when you are performing modal analysis, eigenvalue problem you are solving, which period you are going to get? Depending on what value of EI you have substituted, you can get this or this. Okay, so you can get Ki, you can get Ke, and the corresponding periods. You can calculate Ti and Te, and the ratio of Ti and Te because T is inversely proportional to square root of K. Omega is square root Ky. So frequency is directly proportional to k. Period will be inversely proportional to square root k. So this effective, Te over Ti, you will get like this, and Te you can calculate as Ti square root Ti by K. This you will get from modal analysis. So when you will perform modal analysis, you will get this period. Effective period you can get from here, from the plot of dV versus delta.
And so this Ti, while after performing model analysis, I will consider only for fundamental mode.
Yes, here everything
Is for fundamental.
fundamental mode in that direction. So like that you can get the elastic displacement. This is your first guess of the performance point.
This first elastic displacement getting is corresponding to Ke. That Ke line will I will extend up to when it will get interested.
Right.
Ke.
TE line we will extend like we have done. So in SA versus SD, this is not K, this is T.
Yes.
But it is representing K only.
Yes.
So you extend this where it will intersect your 5% and response spectrum. That displacement will be your guess, a good guess of performance point.
Then after intersecting that, I will find E and ES naught from that, and then the equivalent, and then I will reduce that response spectrum
Right.
down.
Right. Sorry, I missed T here.
But sir, while reducing that response spectrum by some constant value xi equivalent, that response spectrum should go like this, but it is shrinking. Why it is shrinking?
Well, you will, if it is not shrinking, no problem. So you can see simply like this. Let's take a simple case. For EPGA equal to 1, let us say EPGA is equal to 1G. So this value will be 1, this will be 2.5, this will be 1 over T.
Yes.
Okay, and this period will be how much? Where 2.5 and 1 upon T intersect. So 2.5 is equal to 1 upon, let me call this as, this period as TA, this as TB, and this as TC or TL. So 2.5 is 1 upon TV. So TV is 1 upon 2.5, that is 0.4. Now let us reduce this by 0.75. So this will be reduced to how much? 2.5 into 0.75 is how much?
1.87.
1.875. Let us reduce this also by the same factor. So how much is this? 0.75 divided by T. So this intersection will be how much? Let me call it PV dash. So 1.875 is equal to 0.75 divided by TV dash. So how much is TV dash? 0.4. So in this case, when these two factors are same, this period will remain same. But suppose this and this was different. In some of the models, the reduction in velocity control range is different and this acceleration control range is different. In that case, this will be. So if this factor is same like one we are using, then this will remain same. But if these factors are different, this is reducing by a different factor, this is reducing by a different factor, then it may change.
Then for second iteration, how to get that second iteration, that SD2?
SD2 we will take from the originally assumed SD1. Okay, so we had assumed SD1 here, and the intersection we got was somewhere here. So I will choose in between these two. Between these 2 points. Maybe middle of the two if I do not have any better test. And then I will repeat the same exercise here.
Still what? When I confirm that I should stop now.
When the assumed point and intersection point are matching.
But how to know that? How to know that zoomed point and intersecting point are now matching?
Because you know the displacement. Here and here you can calculate it. Okay. So you can calculate displacement corresponding to intersection point, and you already know the displacement corresponding to what you have assumed. So you will know that whether those are same or not, or those are close or not. Okay. So this method is ACC 40 method. This is iterative method. Okay. So this method was further modified in Semaphore 40. That is also iterative method. I am not teaching you Semaphore 40. If anybody is interested, can learn in Semaphore 40 document is also available. You can learn there what changes are there. Okay. There is another type of method based on similar principle, but it is not iterative. Okay. And that is equivalent linearization. So you are familiar with the equation of motion, mx double dot, okay, plus cx dot plus kx is equal to minus mxg double dot. This is the equation of motion of linear system. Of linear SDOF subjected to earthquake shaking. I can also write this equation in the form x double dot plus 2 xi omega n, okay, x dot, I am dividing it by m, plus omega n square x is equal to minus xg double dot. This is for linear elastic single degree freedom system. What does that mean? That the single degree freedom system has the, if I apply a force here and I calculate the displacement delta, then F versus delta is a linear, and this is K. Now, if it is non-linear system, then what will happen? This F versus delta will be non-linear. Can you write down equation of motion for this non-linear system? Where will be the change?
In place of
Equation 1, let's take. In equation 1, is there any change? So here you have assumed F is equal to K delta or Kx. Let me call it. this as x. Okay, I have used x there, so let me call this also x. So f is equal to kx is substituted here. What will happen here if it is non-linear? I can't substitute f is equal to kx. In place of that, I have to substitute f as a function of x, whatever function it is. Okay, so my equation of motion for nonlinear SDF system mx double dot plus cx dot. In place of kx, it will be f, a function of x. Rest will be same. You agree? Will C remain same? M will remain same, no doubt. With nonlinearity, nothing will happen to the mass. Force definitely will change. You have seen it's no more kx. So I have written the actual force, whatever it is, whatever this graph is giving. What about C?
It will also change.
It will change.
Yes.
Why?
Because change in stiffness is due to the cracking of the section and all those things. So if the cracks are changing, then damping has to change. That's why C has to change.
Okay. So value of C will increase, slightly increases. Okay. But when we have done linear system also, we have considered that value of C which will occur under cat condition. Because damping depends upon how much is the amplitude. To some extent, damping depends on the amplitude. Initially, if you give very little, suppose these buildings are vibrating under ambient vibrations also. What are ambient vibrations? Due to wind, due to traffic, okay, due to any blast, if it is occurring in our nearby cantonment, they do some testing, so some blast will be there. So due to that, some vibrations will be occurring when the vehicles are moving on this road. But the amplitude of those vibrations is very, very low. You can't sense those. If you put a very sensitive accelegraph, okay, then you will get, you can sense that. But otherwise you can't sense it. So amplitude is very small. There the damping will be less. At the time of earthquake, there will be significant deformation. There damping will be more. But will it consist of the hysteretic damping also?
Yes, because it is going in non-linear range now. So we have to consider that also.
No. Hysteretic damping is not to be considered here. Hysteretic damping will be considered by this value of fx. Because this fx will follow this part. So that will be automatically considered by fx. This does not include hysteretic damping. So it will be same as in the previous case. Hysteretic damping here will be considered by this fx. Because fx during loading and unloading is going to be different. For the same value of x here, you take one value of x here, you can see there are two values of f. So while loading, it will use this value of f. While unloading, it will use this value of f. So hysteresis will be automatically considered. Now if you have to solve this equation, you know the solutions. You have done in theory of vibration. Suppose I have to solve this equation. How can I solve it? Can I solve it by assuming x? Earlier, how you solve differential equations? The equation of motion is second order differential equation, ordinary differential equation. What is the solution of such equations? A sin omega t plus b cos omega t. We have done that. Can I solve it like that? By assuming x is equal to a sin omega t plus be cos-omega t? No, because here it will depend what is the form of this fx. Okay, there this equation was homogeneous. This was k into constant times x. Here this may be any order of x. We do not know. So here the solution like that is not possible. You can perform a non-linear, step-by-step integration, numerical integration you can do. So where you know the value at different values of x, you will substitute fx numerically. So a numerical solution is possible. Okay, direct solution of the differential equation is not possible. But what we will do, we will represent this by an equivalent linear system. In this equivalent linear system, we are writing it like this. This we will write 2 xi equivalent. Okay, omega n x plus k equivalent x is equal to this xi equivalent and k equivalent. These are to be obtained in such a way that the value of x should be same. The value of x I will get from numerical solution of this, and because this can be solved now same way as I have solved the linear equation. Only thing is I should know this xi equivalent and k equivalent. So if I can calculate xi equivalent and k equivalent properly, if I know some method by which xi equivalent and k equivalent can be calculated, then the solution will become very easy. Same as I have used for the equation of motion for linear elastic system. In the same way, I can calculate this. The trick is to obtain this xi equivalent and k equivalent.
So this xi equivalent is same as that formula we have used earlier, xi is plus xi.
We will come to that. At the moment, we are just doing this what this xi equivalent and k equivalent is. We have to somehow obtain xi equivalent and k equivalent. Yes. M से divide कर दिया, हाँ, right, you are right. So it won't be k equivalent, it will be k equivalent by m. So that will become omega equivalent square. And this also will not be omega n, this will be omega equivalent.
Sir, this xi equivalent is of elastic plus hysteresis. Xi equivalent.
Right. This will now this xi equivalent, because here we are not considering hysteresis in the force.
No, we are
Okay,
considering
so-
because we have substituted f of x as some function of omega square x. Like x is not constant. So there we are considering
Actually, it is a variable. We have represented it by a constant.
omega square.
So when I am representing it by a constant, let us say here, I can draw a line like this.
Yes.
So this is equivalent. So what it can do? It can represent the value of stiffness at this point or any other point. I can draw it here also.
Yes.
So it is possible to represent the stiffness like this at that displacement, but it can't represent the hysteresis. For representing hysteresis, I have to use the full function of x, which will have different value in loading and different value in unloading.
So we can do that this capacity curve, non-linear curve, we can convert it into bilinear.
Even then I can't do that, because if I convert it into bilinear, Suppose I am using a bilinear curve. So this is loading. When unloading will start, it will follow this curve. So same value of x, I will have again two values of x.
Can we, my son is like we can do that key up to linear point, we have one problem, and then after that non-linear point, we have
Actually, up to linear point there is no problem. That solution you know very easy.
Yes.
So if your displacement is restricted here, up to here only, then there is no issue. All problems start because in earthquake our displacement is beyond this point. If we had to solve only this problem, then there is no issue. But actually we have to solve this problem. So here, at any displacement, whatever displacement I take, I can draw a secant stiffness line like this. So I can calculate a secant stiffness at this displacement. Okay. I can call this as my K equivalent. Or any other value also I can take. But what I cannot represent by this is the hysteresis. Linear system cannot represent hysteresis. So the energy dissipated during hysteresis, I have to represent in some different manner. And how I am doing that? That I am doing through this xi. So this xi equivalent includes xi naught plus xi hysteresis.
But sir, अभी आपने बोला था which that middle term does not include the hysteresis damping.
In linear system. In linear system it does not. In linear system, C does not include hysteretic damping. Because there is no hysteretic damping there. So this side and this side equivalent here are different. In what way? That this xi equivalent also has to include the effect of hysteresis. Okay. So the simplest way of this equivalent linearization method is that we declare K equivalent is equal to K secant and xi equivalent equal to xi naught plus xi hysteretic. And how we can calculate xi hysteretic? 1/4 pi dV over S. And period we take as secant period. Suppose my F versus X curve is bilinear. This is K E, not equivalent, effective, which it takes into account the tracking. You can as well say is as Ki, okay, and this is alpha times K. So at different displacements, you can see that secant stiffness is going to be different. This is Kc or K equivalent. So K equivalent is going to be different. K equivalent is function of X. This is, let us say, yield displacement, okay, and at any displacement x, I can calculate the ratio of these two, mu, okay, as x over x at E. So, can you calculate this K secant or K equivalent in terms of KE, okay, and mu and alpha? So, this K equivalent is equal to K secant, that is equal to, let us say this was Fy, this let me call it Fu, okay, and this displacement is x or xu, let me call it. So that will be Fu over xu. Now, can you tell me Fu in terms of Fy? Fy plus
alpha times K.
alpha times what? Ke into
xu minus xy.
agree? So Fu you can write down as Fy is Ke times xy. Plus alpha times Ke 1 over mu, that will divide by xy. So 1 over mu minus 1 into x. Agree? So Fu over xy, this is equal to Ke 1 plus alpha into 1 upon mu minus 1. Right. Not 1 upon mu, it is mu. Xu over xy, xy I have taken out, so this will be mu. You agree? And Fu divided by mu times xy. I will divide this also by mu, I will divide this also by mu. So that will be Ke 1 plus alpha mu minus alpha over mu. What is this? Fu over mu xy. Mu into xy. Xu. So this is your K secant. K secant is Ke 1 plus alpha mu minus alpha divided by mu. Then T equivalent is equal to square root 1 upon 2 pi m over square root of k equivalent, that is k secant, and TE is 1 upon 2 pi, 1 upon 2 pi or 2 pi omega 2 pi by t होगा ना, so it will be 2 pi, not 1 upon 2 pi. And t is 2 pi square root agreed. So T equivalent over TE, this will be equal to the square root of KE over K. So T equivalent will be equal to TE, the square root of K equivalent by KE from this equation. This is K equivalent, so K equivalent by KE will be what? This, the square root of 1 plus alpha mu minus alpha divided by mu. उल्टा होगा, this is KE by K equivalent, okay, not K equivalent by KE, KE by K equivalent, so this will be opposite. So it will be mu over 1 plus alpha mu minus alpha. Okay. So for elastic perfectly plastic, what is elastic perfectly plastic system? Which has this type of load versus displacement system behavior, where this is horizontal. This we call elastic perfectly plastic. Here you can see that alpha is equal to 0. So what will be T equivalent in that case? TE square root so the equivalent period depends on the initial period or effective period into square root of it. Okay, so if I plot this F versus S, I can also plot in terms of SA versus SD as I have done earlier. Okay. So depending on this value of SD, there will be different periods. So the equivalent period will change. Okay. So as mu is increasing, T equivalent increases in proportion to the square root of ductility demand. Larger ductility, longer will be the period. Okay. This phenomena is called period elongation. And if the ductility demand on your structure is 4 times, ductility demand is 4, then period will increase 2 times. The period will become 1. So this phenomena is called period elongation due to ductility demand. Ductility demand means if ductility demand is equal to 1, what does that mean? The structure is elastic. In that case, T equivalent will be equal to TE. Mu is equal to 1. If mu is equal to 0.5, elastic. In that case, what will happen to T equivalent? You have to keep in mind this is valid only for inelastic structure. Mu greater than 1.0. Less than 1.0, T equivalent will be TE. Only for that it will be more than. Yes.
Because of the ductility, the energy dissipation. That's why the energy dissipation in the system has cantilever into some energy because of cantilever. That's why its stiffness will change.
But if the depth is increasing, why the stiffness will reduce? So it is not because of the dissipating energy. It is because your structure is becoming flexible after that. So if your structure has yielded, the structure will become flexible. Stiffness reduces. And when stiffness is reducing, see after yielding of any structure, what happens? 2 things happen. One thing is that this stiffness changes. Second thing is that the loading and unloading curve are different. So change in the stiffness, what it is leading to? Reduction in stiffness, elongation of period. And what is loading and different loading and unloading? What that is leading to? Additional damping. So additional damping or energy dissipation arises because loading and unloading curves are different. If loading and unloading curves were same, even if it was non-linear, you think of a non-linear elastic structure. So what will happen? What will be the load displacement curve? Non-linear elastic. In non-linear elastic system, this is non-linear, but loading and unloading is occurring along the same path. You can represent this also by equivalent bilinear. So here also you can see that stiffness is going to change. This stiffness is different than this stiffness. So stiffness will reduce, period will change, but chi equivalent will be same as that.
But energy dissipation takes place
How energy dissipation will take place here?
when hysteresis is loading and unloading.
Where will be hysteresis if it is elastic?
Not in the last
That's what I am saying. That if it is non-linear inelastic system, which is usually when we say non-linear, we mean non-linear inelastic. But you should be clear that actually we mean non-linear inelastic system. So in non-linear inelastic system, two things are happening. One is that the stiffness is changing, which is giving rise to period elongation. The other thing happens that hysteresis happens due to additional energy dissipation happens. That we are taking into account through xi.
That's responsible for the amplitude
That is responsible for
decay.
amplitude decay of what?
Response amplitude.
No, it does not decay. It remains same or it may be more. Amplitude does not decay.
But
Amplitude of elastic and inelastic structure either remains same or inelastic has larger displacement. Response of elastic structure is not less than that of the elastic structure. So this damping, don't think that because of this damping the amplitude is going to reduce. Amplitude is not reducing.
that means when in non-linear inelastic range, the energy dissipation means energy means resistance force is more.
In
If energy dissipation
resistance force is not more. Resistance force is less. Because if resistance force was more, it would not have needed. Okay, let's think it like this. Elastic structure, let's first take.
yes,
Linear elastic structure. What will be the response?
yes.
In elastic, let us say this is the force, this is the displacement. In elastic structure, what will happen? Okay. This one. So here what is happening? The period has increased because the stiffness has reduced. If it was elastic structure only and period has increased, what will happen to the displacement?
It is elastic structure.
If it is elastic structure, period increases, what will happen to the displacement? Under a given earthquake. Why? You know SD versus T relationship for a given earthquake. So given earthquake, if you plot response spectrum, you know SD increases with T. So if this system was becoming only flexible, no energy dissipation, non-linear elastic structure, non-linear elastic structure, energy dissipation was not increasing, but only the period was elongating, then its displacement will increase. But fortunately here, energy dissipation is also increasing. So what is happening? The amplitude is reducing from what it would have been increased to. And finally, interestingly, it brings it to more or less same displacement, which was there in the elastic connection. Okay, so this energy dissipation should not give you a misconception that it is going to reduce the amplitude of motion of inelastic structure. In elastic structure, period increase would have resulted in increased amplitude. Energy dissipation causes reduction in amplitude. The resultant is such that it is more or less same as in case of elastic structure. Okay. So let's also calculate the equivalent damping for the same case. let's calculate. E. ES and y hysteresis, that is 1/4 pi ED over E. Please.
So it's a perfectly classical. That line is perfectly classical.
Yeah, I have taken alpha is equal to 0 to simplify the calculation. Once you do that, you can do it with alpha non-zero also. ये वाली लाइन इसके पैरेलल होगी, अलग बनाना, अदरवाइज बाद में कंफ्यूजन। This line is parallel to this line, and this line is parallel to this line. You can calculate area of this one parallelogram 4 times of that. Is displacement is 7.
Displacement is reduced because of the
Earlier 5% was kind then you have increased the time.
Yes.
Then displacement is
displacement
good.
is reduced because of the damping.
Right.
And damping is related to the energy dissipation of the system. Means when the gyre is increasing, more system energy dissipation takes place.
Right.
In here, gyre hysteresis include that additional damping in the
Correct.
system. So amplitude decrease also takes place.
Yes. But the amplitude also increases because of the elongation of the period.
Okay.
Because what you have said just now, there you have assumed that the period will increase.
Yes.
But here what is happening?
Period elongation is also additional.
So due to period elongation, it is increasing. Due to hysteretic damping, it is decreasing. Both compensate for each other, and finally you get the same. You can use a simple geometric theorem. What is that? That area of all the parallelograms between two parallel lines are same. You might have done in high school. If I take the same base and draw different parallelograms this parallelogram. I can draw another parallelogram. So this area and this area are same. So the area of the rectangle will also be same. So you can calculate the area of the rectangle having same height and same base. It will be same as that of the height. That will make your calculation easier. So ED will be 4 times area of one parallelogram, and area of one parallelogram is how much? Base width. This base width is same as this. And how much is this? And how much is the height? And how much will be ES naught?
Half into xy into
Half into
xy into
Fy into
x.
ES naught is, those who have not understood it, ES naught is just this. Triangle, area of the triangle. Half into height into base. So can you calculate psi hysteresis? Substituting in this formula.
So we considering use not is the damping when our structure is
No, it is not damping. ES naught is the energy which the equivalent system, equivalent elastic system, equivalent linear elastic system is storing when it is given the same displacement. So equivalent system is this.
yes.
It is given up to this displacement, so the energy stored is how much? Elastic system stores the energy, and when you remove the load, it will give you back. So that is equal to the area of the load displacement curve. And inelastic system is dissipating the energy. How much that is dissipating? Equal to the area of the load. निकाला देवल? अरे numerator में तुम क्यों आएगा? Actually है ना numerator.
2/5 into 1 minus 1.
Right. Is everybody able to get this? Anybody who is not able to get? This is hysteretic damping in ideal case, ideal hysteresis loop. What is ideal hysteresis loop? When loading and unloading occurs along the parallel paths, that we call ideal. I have shown you in the last semester and maybe here also actual hysteretic loops. This is more or less, this is the actual. This is the hysteretic loop of an ideal structure. A steel structure, the material is ductile, we know steel is ductile material, and the detailing was also proper. Then we will get something like this, and here you can check that this is more or less ideal. Although more or less, still not perfectly parallelogram, perfect parallelogram like this. It is also not perfectly parallelogram, but closest to the parallelogram. Okay, this is also not ideal. But if you look at this, is it parallelogram? This is concrete. So you can see the parallelogram would have been like this, or rather like this. This would have been the parallelogram. So here the area is much reduced. And what is this called? Pinching. So due to pinching, the area of the hysteretic loop will reduce. And if area of the hysteretic loop will reduce, what will happen to xi equivalent? It will reduce. That we have obtained 2 mu minus 1 over mu pi, that is in ideal condition. In real condition it will be less, and we can say that in real structures this xi hysteresis will be some constant c mu minus 1 over mu pi, and c will be less than or equal to maximum value can be equal to. In ideal condition, C will be equal to 2. Other cases, it is going to be less than 2. Priestley has given this value of C for different types of structures. Studying their experimental systematic behavior, they have come out. I mean, Priestley actually is representing a big group. So, different papers published by different people in the group. I have taken from his book, DDBD, Direct Displacement Based Design. Okay. So, there you can find it for concrete frame buildings. Xi equivalent is Xi naught. Xi naught is 0.05 plus 0.565 in place of 2, mu minus 1 over mu bar. For concrete wall, that means shear wall, buildings and bridges which are behaving more or less like cantilevers. Bridge pier is also like a cantilever, shear wall is also like a cantilever. There it is further less. Xi equivalent is 0.05 plus 0.444 mu minus 1 over mu. And for steel frames, as you can expect, this is maximum. Okay, so Xi equivalent you can calculate like this. T equivalent we have already calculated. Agree? And R xi also I have given. This makes our calculation very simple. Using the same response spectrum, we can obtain the response of nonlinear system also. How? This is our SA versus T. Response spectrum for 5%. What we can convert it? We can convert it into SD versus T for 5%. Let us say I calculate the equivalent. Anything 20%, 25%, 15%, 30% depending on the value of mu. Okay. So I can for the equivalent. My TE was somewhere here. I would have calculated SAE and I could have calculated SDE as SAE into TE square divided by 4 pi square. You can read that directly from here also. This is our TE. What will be our T equivalent? We will calculate from that formula. Okay, if alpha is 0, it will be simply T square root mu. Okay, but I will calculate from this reduced. This will give me as a SDE is on the original response spectrum from the original period. Elastic response spectrum using elastic period. Okay. Nonlinear responses on the elongated period and on the reduced response. And this is say R by product. This method is called equivalent linearization. And not one method is available. So many methods. People have tried different values of psi equivalent and T equivalent. Okay. The most developed is Priestley's method, which I have given. There will be changes in these expressions. Any question? That SDP is the performance one. The displacement corresponding to performance I is the displacement of a non-linear system during given a the displacement which will actually occur in my system during given. If I am happy with this SDP, okay. If I am not happy, I think performance is not good, then what should I do? I have to improve the design of my structure. Okay, so let's go back to our original pushover method when we were doing. We have taken force proportional to the first mode. We have calculated base shear. And Qi is proportional to phi. Then we calculated displacement, delta phi, which is also equal to delta v. And then you recall we have calculated or we have plotted base shear versus delta root. Okay. This curve we got. So we got a yield here. Then we got a yield here, yield here. What happens after yielding? When a member yields, then what happens? It will have plastic deformation. Plastic deformation initially will be small, then it will increase, it will go on increasing, and finally it will fail. And At a member level, we have plotted m versus theta curve, and m versus theta curve was something like this. In AC 41, this is our backbone curve. In AC 41, this point is A, B, C, D, and D. Somewhere here in a member, we were getting immediate occupancy I. Let me use a different. Somewhere here, let us say I am getting I. I have used green color. Means very nice. Damage is very limited. IO type of damage, what does that mean? The damage which is not visible even with naked eye. Okay, yielding has occurred, but the plastic deformation is small. When yielding has occurred, some cracks will be there, but those cracks are fine cracks. You will not be able to even detect that damage with naked eye. Okay, so that situation we call IO. Then if the displacement increases further, we get somewhere here, like this. What does that mean? Some concrete is falling. Okay, damage is very much visible now. Okay, but large concrete portions are not falling, which can cause fatal injury. And here we have it will collapse. So in my building also, that beam which yielded first, that might have reached CP. Some other beam may be LS. Some other beam may be I. So at some roof displacement here, I am going to get I. Some other displacement, when displacement increases further, some other point will reach L, and finally when it collapses, it will reach C. And my performance point, which I have obtained here, SDP is, let us say this. This is my performance. SDP I have obtained using either ADC-40 method or equivalent linearization. Actually, ADC-40 method is also equivalent linearization. Okay. That is the easy, but there the equivalent damping was taken simply 1/4 pi AD by ES naught, which is non-negative, which is wrong. Actually, you do not get that. Okay, so that was the answer. So equivalent linearization method, that is correct. ADC-40 method is correct. So we will get this performance point, this displacement. So can you tell me what is the performance of the building? If the displacement is this during the earthquake, what you are seeing in your building? At this point, the life safety, okay, hinges, some of the hinges have crossed life safety, but none of the hinge has crossed life safety. So what will be the performance of the Can I call it IO, LS or CP? Can we call it LS? What about if this SDP was here? Then also it was LS. Some of the members have damage much more than LS. So what will you call this structure? The performance is CP. If a little more displacement occurs, it goes here. What will happen? Collapse. So this is representing CP performance level, not LS. This is representing anywhere between this. Okay, it is LS. Up to this, it is I. So here to here, anywhere, this is I. Here to, sorry, here. This is LS. Okay, here to here, this is CP. And beyond that, it is collapse. As soon as one member has plastic rotation more than what is permitted to LS, then the bending performance level will be declared CP. It has crossed LS. Okay. So now, for any building, if you want to estimate its performance, what will be the steps? Suppose this building is there. You want to calculate its performance during that. What will be the steps? First, you will make a model where not only the sizes of the members will be required, reinforcement of the members will also be required. So that you can calculate MY. Okay. You can calculate IO, LS, A, B, C value from AC 41. Then you will perform a pushover analysis. Pushover analysis will give you the capacity curve and the displacement corresponding to IO, LS, CE formation in any member, in the first member. When the first IO hinge forms, it crosses IO, then the first plastic hinge crosses LS, and the first plastic hinge crosses C. That you will note down. Then, using of either of these two methods which I have taught you so far, I am going to teach you more methods also, two more methods to calculate a performance point. But till now I have told you two methods. Out of these two methods, first method 8640 is obsolete, we know. So using equivalent linearization method, you can calculate SDP and then check whether SDP is in this range, or this range, or beyond this. That will tell you what is the performance of your building. Suppose you are not happy with CP performance, you want it to be LS only, what can you do? You are not happy that it has crossed LS. I want LS. What can I do? Retrofitting for existing building, suppose you are designing a new building. You first do the design using code method, then calculate performance like this, and you are not satisfied with the performance. What will you do? Capacity will increase how?
By changing the reinforcement details and changing the size
How
of
you will change the reinforcement? There are so many columns, so many beams, where you will start changing.
No, this is preliminary design we are doing.
Yeah.
So analysis we are doing in ETAS first. When
After ETAPS, I have obtained, after doing pushover analysis in ETAPS, I got this performance which I am not happy with. Now tell me in ETAPS how I am going to improve the performance.
I will revise the design details.
How?
Because
How I will start revising?
But
This building has hundreds of beams and columns.
yes,
Which beam and column I will start revising?
while
One which has crossed that. Okay, then some other number may cross that.
I will keep iterating till all the elements are not crossing the LS. Once whole design is safe, that is no one is crossing the LS, then I will provide that.
See, you have to follow all those requirements of the code. Strong column beam you have to follow in any case.
Yes.
Gravity load design you have to follow in any case. Okay, so whatever design you have done as a code, that you have to follow. Still you have to increase its capacity. Can you increase ductility? Do you know any method by which you can increase ductility? Energy dissipation? We have already done ductile ductility. What more than that we can do, which is available in IS 1990? Okay. So if I am getting something unexpected, suppose a beam is failing in shear, then you can improve it. If some column is yielding before yielding of the beam, you can check it. But if you have followed all those, then you have nothing to do at the component level. What you have to do? You have to design your building for higher base shear. You will increase your design base shear. Okay. When you will increase the design base shear, what is going to change? Here, or let us say here, what change you are expecting? If I design is for larger base shear,
Delta of cooling.
what will happen to the VV versus delta roof curve? I or the CP will be more or less at the same. Discuss. So how you think the performance is going to improve? Will it help in performance? First of all, tell me what will happen to the period. Will it remain same? If you have designed it for higher base shear, what will happen to the period? Will the period remain same? You have to increase the sizes of the beams and columns. Even if you have not increased anything, you have increased only reinforcement, then in reality the period reduces. Okay, the stiffness increases. Okay, but suppose you have not done that, you have taken the cracked section period, section remains same, it is 0.3, so period will remain same. Okay, what will happen to the energy dissipated? That parallelogram. What will happen to this? This Fi has increased. Even if period is same, at the same displacement, what will happen to the area of the static curve? Same ductility demand. Area of the static loop is going to increase, and when the area of the static loop is going to increase, what will happen to your SDP? It will shift towards left. So your SDP is down here.
So, but area of the aesthetic width of the area of the aesthetic loop will also decrease now. When
You have to keep mu same. So when you are increasing and mu you are keeping same. Okay. So this much increase The ratio of this and this will be same as the ratio of this. This point will go here, and area of the hysteretic loop is going to increase. Okay. So if the area of the hysteretic loop is increasing, the equivalent damping is going to increase, the SDP is going to decrease, and then on this curve you can see that the performance will change from CP to LS. This you have to divide it till you get the required performance. Okay. Any doubt?
Sir,
Yes.
you have made a statement that if a structure will remain elastic, or in other cases the structure will go into the non-linear range, then what the first is that we have made for the estimate for this one, that the displacement is more or less same.
Displacement of what?
Means if our structure will remain elastic, so for a particular demand, some displacement will be. And if our structure
If
is
it is
not
non-linear,
then the displacement is more or less same.
for given us.
For given.
Yes.
But you are saying here that if we are designing for more, so the ratio is changing.
I can explain from that point of view also.
Yes.
This is elastic structure. Its displacement will remain. This is E, this is delta E, response of the elastic structure. In elastic structure, this is delta Y, this is delta U or delta M, and mu is delta M by delta Y, and the plastic displacement is delta M minus delta. Damage will depend on this plastic displacement. Larger the plastic displacement, more damage will be. Now let us, this was our value of Vy. Let me increase this Vy to Vy dash. I am designing for larger force, so Vy dash will be more. If stiffness remains same, this will be delta Y dash, delta U, delta M will remain same according to my statement which you have quoted. So this delta M will remain same. How much will be delta P dash? Reduced. So damage will be. So ductility demand is going to reduce. If you are designing it for higher force, it will yield at higher force, and then the ductility demand is going to reduce. And when the ductility demand is reduced, the damage is also reduced. Okay. So we will stop here, and we are meeting tomorrow then. 12 o'clock. There I will teach you another method of obtaining water. In this period, I have asked you to use 4 different methods. 2 of those methods I have already taught you. 2 more methods